All right, good afternoon. Like you said, I'm Jared Hammond, Senior QC Chemist at SCT. Today I'm going to be talking about amphoteric sulfonates. Specifically, I'm going to be talking about sodium cocoamphohydroxypropylsulfonate. It's kind of a mouthful. I'm probably going to shorten that to CS or amphoteric sulfonate throughout the presentation. We think there's a lot of exciting properties, and we think it is going to be the next generation sulfonate. So, quick agenda, what the talk's going to be. Start off with an introduction to the chemistry, go through the synthesis. We'll hit some mildness data, some foaming properties, and then finish it up with some formulation viscosity. So kicking it off with kind of what is this CS? Well, it is an amphoteric, so depending on your system, it can act either as a cationic or anionic surfactant. It is very renewable with a high renewable carbon index of 79%, and that's accomplished by having both your long carbon chains coming from coconut oil, and in your polar head group, you have vegetable glycerin-based epichlorohydrin going into that polar head group, so you're able to increase that RCI. The product itself and all the byproducts are Prop 65 free. And we found it had extremely low dermal irritation and has a lot of versatility in formulation. One of those other key properties you want to know about your surfactant is the CMC, or the critical micelle concentration. As you can see here, our surface tension, as you add the surfactant, eventually levels off, and you can start getting that cleansing action at about 0.01% active concentration. So if you have a low concentration you need to use in your formulation, we're able to bring that cleansing power. Moving on to the synthesis, real quick, the synthesis begins with a cocoyl hydroxyethyl imidazoline, which you can see has that 5-membered ring, which is the imidazoline group. You start with a hydrolysis with water and some heat, and you open up that ring. So where that arrow is pointing into that ring, you open it up and you end up with a more linear molecule. That molecule is then reacted with the sodium 3-chloro-2-hydroxypropane-sulfonate, which brings in that sulfonate group, but it also brings in those carbons from the bio-based epichlorohydrin. And after those are reacted, you end up with our final product. And here it is again, sodium cocoamphohydroxypropylsulfonate. So moving on to mildness. This is where we had some of the most exciting data that we found. For our mildness testing, we did do Zein. Zein is a yellow corn protein, very similar to keratin in skin and hair. The way the test is performed is you introduce the Zein protein to your surfactant, and if it is solubilized, it indicates a higher irritation. And often scores are normalized to sodium lauryl sulfate, just because it's so irritating. That's given 100, and then you can compare to that. Here is some of our Zein data just for this amphoteric sulfonate. As you can see, depending on the pH, you can get different levels of irritation. In a very high pH, you do have some irritation, but as we move down into those neutral and kind of more personal care formulation areas, you have very low percentage of Zein dissolved. And so it's just a very low irritation. To give an idea of how non-irritating it is, we've just given a quick comparison. So you have sodium lauryl sulfate on the right, which is very irritating, given 100. In the center, we have disodium PEG-12 dimethicone sulfosuccinate, which is known in the industry as one of the most mild surfactants, used in wipes and a lot of leave-on applications. And at a pH of 5.8, we actually ended up with a lower Zein score for this amphoteric sulfonate, which was just very interesting and kind of leads you to think that this product could be used in these monosurfactant formulations like the wipes and leave-on. So, quick example of what you might be able to do. You can have a micellar water formulation. This is one that we brought together. You start off with 3.5% of the amphoteric sulfonate. You disperse that in your water. You can add some glycerin as a humectant and preservative. In this case, we did phenoxyethanol, and then you can adjust your pH with citric acid, and that's just a great example of a monosurfactant system that is a leave-on and can use that mildness. Taking a quick look at some of our foaming properties, and before that, there's a lot of heavy data, so I'm going to be doing some abbreviations. CAPB is going to be for the betaine, AOS, alpha-olefin sulfonate. CAPHS is the cocoamphohydroxypropylsulfonate, and then SLES is your sodium lauryl ether sulfate. And then we also have our amides that we are comparing to, CMEA, CMIPA, and CDIPA. The foaming testing that we did is a Hart-deGeorge foam test. It uses the apparatus you see on the right. It begins with it involves, you have a mesh sieve, and on top of that mesh sieve, you put a funnel with a wire at a specified height. You take your surfactant concentration, we diluted down to 1% active solids, adjusted the pH of that solution to 5 to 5.5, took 100 mils of that, put it in a foam blender, or put it in a blender and blended until it turned into a foam, and immediately poured it into the apparatus. And there's two measurements that we take out of it. The first one is the wire time, which is just the amount of time it takes for that wire that you can see in the funnel to become fully visible. A higher wire time indicates better initial foaming. And then after that, as it drains into the graduated cylinder, we measure foam stability by looking at the drainage over the course of 14 minutes. So as we're looking at this data for wire time, a higher number is better, but when we're looking for drainage, a lower number is better because it indicates better foam stability. When we were first looking into the surfactant and just seeing what kind of interactions we had, we did some one-to-one comparisons, so just taking formulations of one-to-one surfactants and then diluting that down to 1% active for the foaming solution. So looking at these groups, you can see on the left in each group you have the amphoteric sulfonate along with the betaine and the hydroxysultaine. In the center in the green, that's a mixture of the AOS along with the amphoteric sulfonate, and then on the right we just did some comparisons with AOS and the betaine and sultaine. And as you can see, first looking at our wire time, the AOS and the betaine is, there's a reason it's the standard. You have very good initial foaming, but when you look towards the foam stability, you can see that the CS does have some stabilizing properties. Especially you can see interaction with the amphoteric and the betaine. All the way on the left, looking up at the 14-minute mark, you can see it's right up there and actually performs better than the AOS and the betaine. And one of the other great interactions we saw as far as foam stability goes is with the AOS and the amphoteric surfactant. So moving on, we saw that interaction with the AOS, and we wanted to look into that a little bit further. So we started with the formula of 7% AOS, 3% of whatever secondary surfactant we were looking for, and then just 1% cocamide MEA. And here you can see on the left, we have the betaine as the secondary surfactant, and the red is the amphoteric sulfonate, and then on the right we have the hydroxysultaine. And in this case, we did see great performance coming out of this amphoteric sulfonate. Wire times were very similar among the three different groups, and then looking at the foam stability, it's either right there in the pack or it performs even better as the longer period of time that you're looking at. Now taking a look at some of our formulation viscosity. First thing, going to give us a reference for something that we're all familiar with. This is a normal hand soap formulation. You have 7% active SLES, 1.3% active betaine, and 1.5% active cocamide MEA. As you can see, we have a normal, nice salt response, and we're going to be seeing this curve throughout just to give you a reference. And the kind of things that we saw, it looks that the surfactant is going to be an excellent candidate for amide replacement. In an AOS-based formulation, you can replace Cocoamide MEA 1-to-1 and get similar viscosity performance. For traditional sulfate systems, it's 1 to 5 to 1, but because it is a liquid surfactant, you have to have no heating step. If you have a cold blending process, this can be immediately substituted in, and you don't have to have any heating. We also found that by adjusting the activity of the CS, you can very easily fine-tune your salt response in your formulation, and we'll see some data for that. And then we saw a lot of great viscosity synergy when used with AOS and sultaine. So first, taking a quick look at the amide replacement, there's a lot going on the slide. That kind of purplish line is our CS, and our formulation is a 7% active ether sulfate and a 1.3% active betaine, and then looking at replacing amides. So that red line is that same reference that we were looking at on the previous slide, and you can see that the CS is in the group. It has a little bit less salt response, but it's still within 0.25% of salt added. And then continuing along with that, replacing the betaine with the sultaine, we saw some really great performance at the same, with a 1.5% amount of the amphoteric sulfonate, you had a little bit less salt response. If you bump that up to 2%, with the green line, you can see that that salt response easily outperforms the that reference slide that we were, or the reference curve that we were looking at. And with the 1.75% amphoteric sulfonate, you can easily match that line. And this also shows that ability to adjust your salt curve using this amphoteric sulfonate. Some of the best interactions we saw as far as formulation viscosity goes is with the AOS. So if you take a 7% active AOS, 3.2% active betaine, and then have your CS at whatever concentration you want, you can really get some great interaction. So as you can see, this orange line on the left is with a 3% amphoteric sulfonate, and it just blew the viscosity out of the water. So there's a lot of difficulty sometimes with thickening sulfate-free systems, and in this case, you can really have no problem with that. We even brought it down to 2%, and we were still far outstripping that reference that we were comparing it to. And down at the bottom, you can see if you take that reference slide, that reference curve, it's almost completely overlapping, and it's a 1-to-1 replacement immediately. And then this is just looking at, again, trying to see as a secondary surfactant how it would act. And if you have a formulation in this case with 7% active sulfate, and then whatever percentage of the secondary surfactant we're looking at, in this case CS, and then 2% active cocoamphohydroxypropylsulfonate, you can see if we have both of those secondary surfactants as a co-secondary surfactant, we're still far outstripping that kind of reference viscosity curve. And then by lowering it a little bit, we can again match it pretty easily. So just in conclusion, this surfactant is very versatile in both traditional sulfate and sulfate-free systems. It does have that 79% renewable carbon index. It is completely Prop 65 free. It is extremely mild, and that extreme mildness makes it a great candidate for those monosurfactant non-rinse formulations such as the micellar water or wipes. And then looking at the salt response and foaming performance, you can get the foaming performance that you want and the viscosity performance you want in both a traditional sulfate system and a sulfate-free system. Just a quick thanks to all the people who helped me in this process, both in data collection and kind of putting it all together. And I guess if we have any questions. Yes. I don't have that, but we could talk about it after. So she asked if we knew what was it, the EWG, the rating. I don't have that information right now, but we could probably look that up and see if we have it. Yes.
What's the full link you have it again?
Sure. It's sodium. I'll just pop all the way back. For all of our sakes. Oh. There you go. It is quite the mouthful. The sodium cocoamphohydroxypropylsulfonate. Yeah. All right, if there's no questions, thanks for your time.
Thanks, everybody.